Welcome to Tetryonics. In this lecture we'll be covering the quantum geometry of energy momenta and how this produces physical force in our universe. It follows on from the previous lecture where, using tetronic geometries or equilateral geometries, we replaced relativistic terms of force in electrodynamics with geometric explanations for forces. The information in this lecture is contained in spread out through several of the ebooks of Tetryonics, notably ebooks 1 and 2, Quantum Mechanics and Electrodynamics, and these are all available on Google Plus or from Pirate Bay via torrent downloads. Tetryonics itself, based on equilateral geometries, has three main laws when it comes to the physics of the universe. The first one, obviously, is that the square numbers in physics are in fact equilateral geometries, or result from equilateral geometries of energy. It's the geometries itself of the energies that gives us our various physical constants and our quanta of work. Namely, quantized angular momentum is the equilateral geometry of Planck's constant, the angular momentum, and the square root of scalar energy at the quantum level gives us linear momentum, i.e. the quantum of force, or the amount of motion produced for a specific force on matter under Newton's formulation F equals ma. The second law of Tetryonics is that all energy seeks equilibrium. By this, what it means is that energy in all its forms, be it mass, matter, energy momentum, either Planck's constant or linear momentum, and in fact energy momenta itself, as it's expressed as a force, always seeks a state of equilibrium, or a state of least action. This second law is what drives most of our physical interactions on all scales of physics. And thirdly, the final law of Tetryonics is that there are no infinities in physics. By this we mean that the infinities normally encountered in electrodynamics, where mathematics attempts to model scalar forces, for example, by expressing them as a series or an infinite series of smaller and smaller forces, does not in fact exist. What happens within Tetryonics is, due to the finite geometries of the Planck quanta, we have finite solutions for all mass, energy, matter geometries and the forces between them. There's no infinities in any of the mathematical calculations or the geometric solutions for Tetryonics, unless we're expressing, for example, the case where energy follows a geometric pattern and can continue on as far as it likes, so long as the mathematics that describes these geometries follows the geometry. Again, in all cases, the mathematics is simply the language describing the underlying geometry. So you can describe the geometry as the grammar for the mathematics. It sets the rules as what can and cannot be done mathematically. So at this point we have a choice. We can continue to use the mathematics as currently formulated for the various physical disciplines in quantum mechanics, QED, chemistry, cosmology. Some of these obviously model the physical reality very well, but offer us no explanation as to what's creating the physical interactions and the physical geometries of mass, matter, and energy. Or we can turn to the equilateral geometry of energy itself at the quantum level, Planck's constant, and we can use this in lieu of the mathematics to describe and to model all the physical systems. And from there we can then apply the mathematics to describe the final geometries or the interactions that the geometries create. In doing this, as we mentioned previously, the geometry forms the grammar for the mathematics, for the language of mathematics and physics. It sets the ground rules, and as it's a visual medium, it allows us to quickly see the interactions and to model what is going on. In the case of Planck's constant, the quanta of action, the minimum quantum available, it's derived from the fact that energy or scalar energies in all their forms can be quantized within quantum mechanics, and that's Planck's discovery of this constant is what led to quantum mechanics itself. Easiest way to explain it is simply just the dividing of scalar fields, energy fields in all their forms, into smaller and smaller components until we reach a point where we obtain relationships as to how many quanta it takes to create fields of force or mass-matter geometries within physics. The standout point for Tetryonics is obviously the fact that it's the equilateral geometries of Planck's constant that gives us the square numbers of physics. That's to say, square numbers are in fact equilateral geometries. That's represented on this page, obviously with the equilateral geometry being divided up into smaller and smaller quanta, all of identical equilateral geometries. As we increase the frequency of quanta within this energy field, we can relate the quanta to the scalar field through Planck's constant. In fact, dividing the scalar by Planck's constant gives us the Compton frequency, or the number of quanta in the scalar field. Again, we can obviously measure these in a transverse measurement, which will give us h nu, or Bosons, odd numbered geometry, or we can measure them longitudinally, in which case we get photon geometries or 2 pi measurements. And of course the scalar field itself has a square number of quanta. Again, noting that it takes 2 bosons, 2 odd quanta, to form a photon, hf of energy. So relating Einstein's formulation for the photoelectric effect, for example, where spectral lines are produced, to Planck's heat law, h nu, care must be taken at all times to always have 2 Planck quanta giving a photon. They are not a direct equivalence 1-to-1. Of course, with the equilateral geometries reflecting quantized angular momentum, obviously there's a relationship can be drawn up to the classical idea of angular momentum being a vector rotation about a point. Tetryonics shows that at the quantum level of Planck's constant, it's no longer a vector rotation about a point, it is in fact an equilateral geometry that gives us the square meters per second and forms the basis of all mass, matter and energy geometries in physics. This necessitates, of course, the fact that we must move away from right-angled triangle geometries to explain mass, energy, momentum in physics and go back to equilateral triangles. This is one of the key points in quantum mechanics so far as tetronic theory goes. But again, the derivation of all the force laws comes directly from the equilateral geometry of mass, matter and energy, or energy in all its forms. We can obviously quickly show Newton's laws, particularly the second law of force, as an equilateral geometry, and the relationship of F equals ma for the force applied will give us changes in velocity over time, or accelerations. We can relate the scalar energies of any field of force or any field of mass energy to Planck's constant and obtain frequency wavelength relationships for this velocity and the velocity changes. And of course this allows us to define mass, energy and matter within physics on geometric terms rather than mathematical. Of course, in the case of Tetryonics theory, the unified field equation expresses scalar energy as mass alpha nu squared, or mass velocity. The first being Planck's constant. Mass alpha is Planck's constant, nu squared, the number of quanta, or the Compton frequency for the energy of the scalar field. Or this can be re-expressed as a mass velocity squared. There's a one-to-one relationship between the velocity squared and the quantized energy required to create that velocity. Of course, the velocity being the square root of the scalar field. The number of energy momenta, the Compton frequency of the Planck quanta within the field, all combine both in divergent and convergent directions to give us a net divergent force for all scalar fields. Tetryonics obviously follows the equilateral geometry for counting as well as for the geometric interactions of mass energies. And again, transverse odd numbers are quantum levels or bosons of energy, which as they combine sequentially give us square scalar fields of energy. And the square root of these scalar fields is the linear momentum, or the velocity that is created with respect to the matter that's having the force acted upon it. Again, whether you're looking at h nu for quanta of bosons or quanta within bosons, or hf for the quanta of photons within the field, makes no difference. In both cases they form a distribution, or a normal distribution of energy within the scalar field. And this gives us the statistical probabilities associated with quantum electrodynamics. Again, noting that no infinities exist. These are all integer numbers, and there's a geometric relationship between all of the forces and their mathematical formulations, both in classical, quantum, and relativistic theories. There are no infinities, and everything is geometrically related so far as the equations of physics. Planck's constant itself is simply the relationship between how many energy momenta are within the field to create a specific velocity or acceleration of a particle through its energy momenta. Again, the square root of each quantized energy equilateral field within the scalar field contributes to give a net force on any particle through the relationship F equals ma. The classical expression for Planck's constant is mass by quantized angular momentum, or mass geometries. Again, mass being the energy per unit of time, and the quantized angular momentum being the geometry of that energy. It's that geometry, the equilateral geometry, that gives us the charge of any field. It does so because any square amount of quanta within that geometry will result in an arrangement where there is always an excess of either negative or positive charges within that field. Hence we refer to the individual charge of discrete energy momenta within the field as quantized charges, and the total charge of the field as being just the charge, or the net charge. Obviously, calculating for the Planck's quanta per any unit of time measurement, in this case 1 second, will give us a measurement of the energy in kilograms square meters per second squared, or joules. But the key point to take away here is obviously that it's the geometry that's giving us the properties of electric and magnetic fields, and it's the geometry that's allowing us to quantize scalar fields into discrete charged energy momenta. In the case of momenta, of course, I'm referring to not only just linear momentum, but also equilateral geometries of energy, or the quantized angular momentum for Planck's constant. Where these fields interact via the weak force, or the inductive coupling of their magnetic dipoles, we can show that the linear momentum, or the square root of the energy fields, will cancel out where the fields are of equal strengths. If there's an imbalance in the strength when they couple, the energy will distribute until it reaches an equilibrium under the second law of Tetryonics. So there will be an initial motion in the direction where the field is strongest, but over time, due to the inductive coupling of the weak force through the inductive magnetic dipoles, the energy will be distributed in a transformer coupling fashion through both fields, and the particle will come to rest once the strength of the fields is equalized. This results in two distinct geometries being created. So far as force is concerned, we have electrostatic fields and we have magnetostatic fields. The best way to describe these in terms of classical physics is that the electrostatic fields are described with the Coulomb force law, or the forces between charges, whereas the magnetostatic fields are described with the Lorentz force laws, or Ampere's force laws, and it's an interaction between magnetic poles of fields. Again, what applies in the case of static fields in this case has exactly the same interaction and forces as a chem field of energy momenta, in which case we don't have a coupling of the fields, we have a single field. And of course, without the secondary field to act against it, the single field will have a distinct directional velocity created from its number of energy momenta. With the Coulomb or electrostatic fields, the energy momenta within those fields, as illustrated here, will have an effect on any particle that moves within their region of influence. These fields propagate outwards at the natural velocity of energy, or the speed of light in a vacuum, and that velocity is affected both by the medium that the field is moving through or propagating through, as well as the Compton frequency de Broglie wavelength relationships of the energy momenta within the scalar field itself. Frequency by wavelength gives us a precise velocity for any scalar field. Of course, again, the particle that creates the field, in the case of a chem field rather than the scalar field that's shown here, would experience an acceleration under Newton's second law, F equals ma, or a change in velocity dependent on any changes in the energy momenta. In the case where there is no release of bosons or energy momenta from the field, the particle will accelerate to a specific velocity and remain at that velocity until there is a change in the energy momenta within the field, again in accordance with Newton's laws. An object in motion tends to stay in motion unless acted upon by a secondary force. In the case of charged particles that move within the E fields of other electrostatic fields, for example, the charged particles that move into the region of influence will be affected by the discrete energy momenta, or the quantized momenta of the fields itself. In this case, we have a negative electrostatic field on the left-hand side. Any positive charge that moves within this field will experience a convergent force, or an acceleration towards the negative charge. Of course, a negative particle moving into the field of action or influence would experience a convergent force on its negative charges and will be accelerated in the opposite direction. This still applies to matter that's stationary. Its static or non-motionary fields, its blackbody radiation, are comprised of positive and negative fields, and these of course still affect particles as they move within them. and obviously if the field's a positive electrostatic field, the direction of force reverses for the same particles, or if you reverse the charge of the particle, again it becomes a convergent force. These forces can obviously be expressed mathematically in Lorenz's force equations, where the force exerted on a particle moving through, or a charge moving through a field, a charge geometry field of influence, where we have energy momenta, divergent and convergent momenta within that field. The net force on the field, on the particles themselves, is expressed as a function of the electric field component by the velocity of the particle and the magnetic fields as well. Obviously there's two types of momenta involved here. We have the quantized angular momentum, giving us the charge geometries and their arrangement of energy momenta within the specific fields, and we have the square root of the quantized angular momentum, or the linear momentum, which is the momenta of action within the field. Quantized angular momentum is the geometry. The square root of the equilateral geometry is the linear momentum. In both cases they can be described as energy momenta. Of course, depending on whether it's an attractive or repulsive force between various arrangements of charges and particles, we can describe that mathematically, or simply as an expression of the law of interaction. Again, described as interaction rather than strict attraction, because the force may be divergent or convergent depending on the arrangement of charge momenta. Again, the result of the quantized angular momentum of the quanta within the field. Even bar magnets that are normally considered to be magnetic fields only are in fact electromagnetic fields, and particularly they are the result of magnetostatic fields, where we have opposing positive and negative fields creating a enhanced magnetic dipole. At the center, or the block wall, there's obviously a singularity point where there is zero E fields, and a point where the north becomes a south field and a south becomes a north field. Again, this gives us a field of E field energy momenta, particularly linear momenta, within the electric field permittivity of each charge geometry, and it's these energy momenta that create the electromotive force on electrons as you move a closed loop around the magnet itself. And again, because of the geometry involved, as you laterally move up and down the page with a closed loop, the geometry of the field changes in both electric and magnetic field strengths. Again, we can quantize these magnetostatic fields with Planck's constant to give us the Compton frequency and de Broglie wavelength relationships to calculate the force that can be exerted on any electron in the conductor as it moves past or through the electromagnetic fields of the bar magnet. Again, bearing in mind that these fields, as drawn as a two-dimensional slice here in the center of the page, are in fact slices of a three-dimensional field as illustrated at the top right. We can obviously model the quantized angular momentum, the equilateral geometries of the fields, and its quantized energy momenta as a flux of energy, or a electrical rotation of energy about a point within the fields. And this allows us to see the distribution of energy within those fields. But what really shows the how the field applies the force is its equilateral geometry, or quantized angular momentum, in combination with the square root of the equilateral geometries. This then allows us to find the electric and magnetic geometries of the fields and their charges, This of course allows us to see the differing linear energy momenta within the fields and whether they're electric or magnetic in their forces. And of course this allows us to describe whether it's a Coulomb or a Lorentz force that's applied to any particle in a conductor, or any charged particle in a conductor, as it moves about the magnet and through its magnetic field, or in this case it's best described as an electromagnetic field of the bar magnet. As we discussed in the previous 3 lectures, relativity attempted to explain this geometry as a change of the frame of reference between the electric and the magnetic fields, and tried to explain the magnetic moments of electrons as a distortion in the spherical point geometries of charged particles. In both cases, Tetryonics rebuts what special relativity claims and provides a completely alternative explanation through the geometry of energy momenta within the discrete fields, or the scalar fields of magnets as well as electrostatic charges. Again, the geometry gives us the inverse squared laws for E-field strengths and for magnetic pole strengths as expressed as a distance from their sources. This can apply to E fields that are propagating outwards from a point, or EM fields that are propagating out, as well as it applies to a stationary electrostatic or magnetostatic field where you're taking measurements at specific distances from the field. It also shows us why in the case of dipoles we measure a inverse cubed law as opposed to the inverse squared law of the magnetic pole. We can show this geometrically using the quantized angular momenta, and we can draw this as a mapping of the square and cubed laws as illustrated on the left hand side. And of course we can use the square root of the quantized angular energy momenta to give us the linear momenta, or the forces that will be generated by the quanta in each field. We can relate this force back to mass, velocity, or momentum, or we can relate it changes in the energy momenta within this field to changes in velocity or acceleration, and that's what's illustrated on this page. We're looking at the force and how changes to the energy momenta within that field affects both the velocity that it can create through that force for any specific mass under Newton's formulation F equals ma, where the acceleration is described as a change in velocity over time. Again, if the energy momenta of the fields does not change, then there's no change in force, so the particle will experience a constant velocity as described in special relativity, but general relativity is required under Einstein's formulation of these geometries to account for accelerations. Tetryonics explains all of relativistics or relativity's features and formulations through equilateral geometries, and then also explains Newton's formulations for all his laws, along with which are measurements of the linear momenta versus scalar measurements of the same field. In the case of linear momenta, obviously the square of the linear momenta, or the square root, gives us the scalar field of energy, and that can be described as mv squared, again tying back in with this square of momenta, mv just being straightforward linear momentum. So we not only explain Newton's laws, we explain scalar energies and how the energy momentum is created from the quantized energy momenta of the field, and we can explain special and general relativity through this single geometry. Of course, what it also allows us to do is to develop an explanation for inertial mass, because we can calculate for any mass from any force applied. We can measure the acceleration or the change in velocity, and we can model that. Obviously, as we increase the energy momenta within any field, be it a two-dimensional field or a chem field or the charged geometry of matter itself, we increase the frequency and decrease the wavelength of the energy quanta within that field geometry. Again, changes in the quanta produce changes in the quantized angular momentum or the geometry, and also produce changes in the linear momentum in the system. As we increase the number of quanta, we increase the force that can be generated by the net energy momenta quanta within that field. And these, of course, as we just indicated in the previous page, can be used to describe the inertial mass or the mass of matter. Where they refer to the fields, it's inertial mass from the energies. Where we refer to the quanta within the charged geometries of matter itself, it refers to the inertial mass of matter. So Tetryonics gives us exact definitions for mass, energy, and matter, with mass being the number of quantized angular momenta or energy momenta within any unit of time, as opposed to energy being the same but without a time measurement. Of course, in both cases, or in all cases, we can take the square root of the scalar field to give us the linear energy momenta of that field. Again, the angular momentum of the field is the equilateral geometry. And of course, matter is simply a standing wave geometry of mass energies. All of these three forms of energy within Tetryonics that makes up all the energy and the force fields of interaction between the various forms in the universe are derived from Planck's constant. Again, one geometry gives us two types of charge on either side of the equilateral geometry, and these discrete quanta add up to create divergent and convergent energy momenta within any scalar field, giving us our fields of force. A distinction can now be made between kinetic energies and linear momenta and angular momenta. Of course, the quantized angular momentum, or the total angular momentum of any charged geometry, is in fact its equilateral geometry. That scalar field created by the equilateral geometry has a square number of quanta made up of odd-numbered bosons. The field itself has two distinct properties of electromagnetism, being namely the electric permittivity of the field and the magnetic permeability. One's produces a longitudinal force. The magnetic fields produce a transverse force. And again, there's always a dipole created by the positive and negative poles within the charged geometry. You don't find magnetic monopoles. And it is the orientation of the north-south fields within the dipole that determines whether it's a positive or negative charge that is measured. This then allows us to equate back to kinetic energies. Kinetic energy obviously being, or chem fields, being comprised of kinetic energy plus magnetic moments created by the dipole. Hence the term chem field, kinetic EM field, where all the kinetic energies are measured as a half mv square, where the m refers to the mass matter of the object being accelerated or in motion, and the kinetic energy of the field and its magnetic moment are equal in strength, but orthogonally opposed as far as their direction of actions. Of course, we can take the square root of these scalar fields, and we have the linear momentum of the system, or the force that the individual quanta can apply. And this is expressed as momentum equals mv, or mass matter velocity. Again, we can relate this all back to normal scalar fields where the energy is mv squared. The v can obviously represent, in this case because it's referring to mass matter, the velocity, the square of the velocity. Or we can quantize this to express it in terms of Planck nu squared for any velocity. But in both cases, the linear momentum of the system is the square root of the energy momentum within the field, square root of the scalar. And of course, squaring the square root gives us a scalar field. So we show that kinetic energies, magnetic moments, electric field permittivity, linear and angular momentum, mass, energy and matter are all derived from the equilateral geometries of Planck's constant. And this gives us both scalar classical fields of motion and force, and gives us quantized fields of force or energy momenta. We can look closely at these relationships using the equilateral geometry, and we see that in any scalar field, as we've mentioned, any scalar field is a charged geometry because of its quantized angular momentum per c squared, and this gives us a net divergent force from the two directions of interaction within the EM field, the convergent and divergent arrangements of positive and negative charges within the scalar field. We can calculate, as you show here, for energy, for kinetic energies, for the scalar field, for the linear momentum, for the inertial mass of the system, or the acceleration or changes in velocity produced by the energy momenta in any scalar field. This can be an electrostatic field, it can be a chem field, or even it can be the inertial mass contained by the charged geometries or fascia of matter itself. As we change the number of quanta within the field, or the Compton frequency, obviously we change the wavelength of the Planck's constant itself. And if we measure the linear momentum, or the square root of these fields, as a measurement of linear distance, we determine that an increase in frequency, Compton frequency, gives us a decrease in the de Broglie wavelength of the Planck quanta itself. And this is expressed as Lorentz's velocity correction factor. Any change in velocity or any acceleration due to the field or as the result of the energy momenta in the field, or that can be created by the energy momenta in a field, is geometrically related to the force it can apply. More quanta within the field is a stronger force. Less quanta is a weaker force. And as this force strengthens or weakens, the relationship between the frequency and the wavelength changes appropriately for the velocity that's required. V equals frequency by wavelength. Again, all of this shows that the right-angled geometries of classically formulated mathematics in relativity, etc., is incorrect. We should in fact use equilateral geometries. In applying mathematics without the geometry, obviously we develop an erroneous assumption that the speed of light is the limit, and that to increase to the speed of light would require an infinite amount of energy due to the graphing of an infinite series as we approach it. Geometrically, we now disprove that modeling by showing that it's a direct velocity c relationship for the scalar field in its energy momenta. As we increase the momenta, we increase the velocity. So this Lorentz factor can be viewed as an efficiency between the natural velocity that a single quanta can produce, i.e. its natural divergent from a point at the speed of energy, versus how much velocity it can produce with respect to the mass matter it's trying to accelerate. again following Newton's law, F equals ma. So we can calculate for the scalar energy in the relationship between the quanta, the frequency, the velocity, and the mass, and we can determine the Compton frequency is in fact not limited by c, but it can go superluminal. It's a simple geometric relationship between velocity and energy momenta. The natural speed of energy, of course, is the speed of light. And this is borne out a couple ways within Tetryonics. Obviously, the electromagnetic field is the inverse of c squared, as derived by Maxwell's equations, and as shown as a function of the geometry of equilateral fields and energy momenta within them. We can show the geometric relationships between the electric permittivity and the magnetic permeability of the fields, and we show that the square root of these fields, scalar fields, in fact gives us a velocity of c for the permittivity and the magnetic permeability. One by the other, and the square root of it gives us c as a natural velocity of energy. Tetryonics tends not to use the speed of light as the answer, because this velocity will change for different mediums. So it's more appropriate to use the general formulation, which is a velocity rather than the speed of light. The natural velocity of energy is used. Of course, one of the other big points in Tetryonics is where we define mass, matter and energy and apply it to charged objects in motion, particularly as it refers to special relativity. Where a static particle mass matter geometry is created, the mass energy or the energy momenta content of that particle remains in motion, but it's in a standing wave geometry, and this is what gives us our three-dimensional substance to matter itself. So all matter can be described as energy within a spherical coordinate system, or c to the fourth for volumes. Again, it's all matters referred to always drawn mathematically as a capital M versus the lowercase m for mass, so we can distinguish one from the other. Relativity will put mass, matter and energy all into the one stress energy tensor. Tetryonics separates them out and describes them with respect to each other and to the coordinate system used to measure the fields or the energy in all its geometries. We can then obviously calculate for rest mass matters geometries and for the fields that create motion within these fields. Again, we can have electrostatic fields where two chem fields come together and their linear momenta cancels out, or we could have a chem field as drawn at the bottom of the page in the center, in which case it's worth noting that the kinetic energy portion of the chem field again is a photon field, and the only difference between the photons or the photon geometry in the chem field and that of an electrostatic field is that in a chem field it produces a unidirectional acceleration or change in velocity, whereas in an electrostatic field the energy momenta cancel out to produce no motion. Again, because they're a longitudinal field, we can describe them using E equals hf, or we can describe the changes of energy or quantum levels in terms of h nu, because they are changes in bosons. Bosons are released in odd-numbered quanta from the square-numbered field to give us our changes in velocity. Mass, matter and charge itself is invariant to velocity changes. What changes is the Compton frequency and the de Broglie wavelength of the mass energies within the chem field itself. And of course any change to the linear energy momenta and the quanta of these energy momenta within a field produces an acceleration or a change in velocity over time. But in all cases, chem fields follow the same formulation as do most EM fields or scalar fields, and that is mv squared. the only difference being a purely scalar field would be mass velocity squared for its energy momenta, whereas in the case of a chem field it's matter or mass matter velocity squared, because it's F equals ma and the mass is referring to the mass of the matter geometry. So we use a capital M for matter that's being accelerated to a specific speed as a result of the square energy quanta within the field. So using the tetronic geometry to describe force, we not only describe the action of force and the forces that are available for a set number of quanta within a field, we can also relate it back to inertial mass for that field and apply the same thing to the charge geometries of matter to give us a calculation of the inertial mass properties of any matter geometry. And this becomes extremely important when we're talking quantum gravitation, for example. The ability to distinguish between mass and matter and energy in all its forms is critical to understanding gravitation. Again, irrespective of what field you're describing, the energy momenta of each charge geometry or each field is described through E equals mv squared, or its quantized equivalent, h nu squared. We can of course now, having disproved relativity in the previous 3 lectures, change from a spherical point charge to the tetronic geometry of an electron, which is a 12 pi standing wave geometry. And of course we note that it's a standing wave, so the mass matter or mass energy matter of this geometry remains invariant to acceleration of the particle. When force is applied to the particle by any means, the particle itself will have changes of energy momenta within its chem field. Again, the chem field contains kinetic energies, both in longitudinal energy momenta as well as transverse magnetic moments. As the energy quanta increases within the field, the magnetic moment becomes stronger and stronger. The kinetic energy, or the electric permittivity, remains neutral because of the charge geometry of quanta within it, and the fact that it's a two-dimensional field, so the opposite side of this negative charge field would in fact be a positive, and the opposite of the positive would be a negative. So in all cases, irrespective of how you measure it or what direction, even if you change the frame of reference, as you look at the field or try to detect it, you will detect a neutral field. But as the energy momenta increases, the force that the energy momenta within the field creates changes in the velocity of the particle itself. This is referred to as the wave component of wave particle systems in electrodynamics, or in QED. Again, we can draw these with tetronic geometries. We can draw the physical representation as shown here for the relativistic mass energies of the system being studied, or we can draw it as a schema, a simplified schema for the same particle using equilateral geometries. But in both cases, as we add a force or energy momenta to the chem field, we create additional mass energies in the chem field, but the mass energy of the matter remains the same. Adding the two together, we can see that the Lorentz corrections for velocity apply only to mass energies within the chem field, but the combined mass energies of both the matter and the chem fields gives us the relativistic mass energy of the system being studied. As we increase these energy momenta in the chem fields, we create changes in the velocity or accelerations in particles themselves. And again, we can express this using mv squared or hf calculations, or h nu squared for energy momenta in the chem field. And that's what's shown here. As we increase the quanta, we're storing more and more energy in however we choose to measure it in the field, and it creates a corresponding velocity based on the force that the individual quanta can apply to that particle. These changes obviously can be described mathematically, and the formula used to describe them is Rydberg's formula for spectral lines. Again, this has been rewritten in Tetryonics in terms of the differing geometries, or in the case of fractional changes to the scalar M field. But the mathematics still remains correct. In Tetryonics we just show it geometrically rather than mathematically. Of course, this completely repeals what special relativity or relativity's explanation for how magnetic moments are created. In relativity, the magnetic moment is created through the distortion of spherical point charges due to their acceleration or velocity within any field. Tetryonics, we show this as being simply the result of energy momenta within the chem fields, producing a force on the particle. And half of the chem field is the magnetic moment. So as we increase energy by applying a force to the particle, we develop a magnetic moment in proportion to the velocity. There is no distortion of the charged geometries, and should you remove the energy in a chem field, so you have no chem field in your modelling, you'll find that a charged geometry produces neutralized magnetic poles, so it would appear as though there's no magnetic moment on electrostatic point charges. And when those charges have motion, they then develop a magnetic moment. This obviously is completely different to the relativistic explanation in special relativity, but the charged geometry applies everywhere throughout physics, and this is obviously the true explanation for how we generate Bohr magnetons, etc., and other magnetons due to motion or particles in motion. Of course, we can always determine, using tetronic geometry, to determine the Bohr magnetons in relation to the mass matter and the force applied, F equals ma again, and we can compare differing inertial mass matter geometries to the same energy in the chem fields and see that they produce differing strengths of magnetic moments. Again, this is described traditionally in quantum mechanics and electrodynamics as the mass-charge ratio, and shows that the electrons are more efficient at creating a stronger diamagnetic moment for the same energy applied to the particles themselves. Obviously, the difference being the inertial mass energy quanta within the charged geometries themselves, F equals ma. In the case of energy momenta within fields, we can obviously quantize this using Planck's constant, and the electrical properties will give us a measure of charged mass geometries, which of course is just a measure of the equilateral distribution of energy within the field itself, but it can be modelled using a vector rotation, as quantized angular momentum is often thought of being. But it's the Compton frequency, or the number of quanta within any field, that determines the strength or the amount of force that can be generated by that field. And of course we can measure this in terms of quantum levels or transverse bosons, or we can measure it longitudinally in terms of force generated by the field, or the energy momenta within the field. And as we look closely at the energy momenta side of things, or the linear measurements, square root measurements of the scalar fields, we can see the force vectors for the electric and the magnetic fields pop out of Tetronic geometries, and we can relate the number of quanta, or the net scalar energy momenta in the field, to both the linear and the charge of the field, the linear momentum of the field, or it's the force that it can exert, and the charge of the field, its equilateral geometry. We can write all this in terms of energy using the unified field equation, where energy is written as mass alpha nu squared, or Planck nu squared, and can be reinterpreted as just mass velocity squared as well. What this shows us is that the alpha, or the equilateral geometry of mass energy quanta, is what is the hidden constant within Planck's constant. We can obviously continue this analogy through from two-dimensional fields, 2D mass energies, to the energy, or the mass energy stored within matter itself, or three-dimensional standing waves of mass energy. In which case, the mass energy of 2D fields is in fact the mass energy of the fascia of tetronic geometries, or matter. And again, while it produces no force of motion, it does produce forces within the charged geometry of matter itself, and that's what gives matter substance and solidity. Where we look at two-dimensional fields, we can use the two-dimensional fields and the orientation of their Planck energy momenta in both forms to give us an explanation of electricity, or electrical power, electrical forces. Obviously, the scalar fields, through their equilateral geometry, or their quantized angular momentum, gives us charge masses, and these charged masses go on to interact via the weak force to form charged matter geometries, standing wave energy momenta. If we separate these charges, or the charged fields, the energy momenta within the each charged geometry will give us a voltage, or the potential to exert an electromotive, or create an electromotive force on charged particles within the field. We can use these fields for separated charged particles to give us Coulomb's law of interaction, where the chem fields of the charged particles, or their electrostatic fields, give us an interactive force between the charges. Or we can simply separate the charges onto plates, for example, within capacitors or batteries or generators, and then connect the two separated voltages with a conductor, allowing the electromotive force to seek equilibrium under the second law of Tetryonics. In doing so, it will create an electric field within the conductor, where the energy momenta stored in the voltage within the charged geometries will spread out through the conductor, energize it or electrify it, and in doing so, any charged particle in the conductor will gain energy momenta in its chem field and begin to accelerate. And we can obviously measure the motion of these charged particles in the conductor, and this is what we call current. We can measure it in terms of the force of the charge, or we can measure it in terms of the number of charged geometries going past a particular point per unit of time. Obviously, in the case of electricity, it's the energy momenta of the electric field that's applying the force on charged geometries, and it's the arrangement of the linear energy momenta in these fields, the positive or negative charges, and their linear divergent or convergent directions of force with respect to any particular charge, i.e. whether it's a sink or a source with respect to the electrical properties. It's these energy momenta that create the force, or exert the force, on the charged particles in the circuit, and again it's proportional to the number of quanta within the electrified conductor or the voltage of the charges in the circuit or the battery. The higher the energy momenta within the charge plates, the higher the voltage or the EMF between the plates to drive a current. But again, noting that the electrical field flows first, nearly instantaneously, as it seeks equilibrium, and once it's established, it's the energy momenta of the electric field that drives the motion or creates the motion of the charged particles in the conductor, and these particles move considerably less than the speed of the electrical field because they have larger inertial mass matter geometries. And of course, once they are in motion, their chem field energies will create a magnetic moment, which is described with Ampere force laws and Lorentz forces, right hand, left hand rule laws, where we're describing the magnetic field created by a current in a conductor. Again, this magnetic field created around the conductor is the result of the chem field energy geometries of the charged particles in the conductor. So we can add energy via the voltage sources. All we're doing is adding energy momenta from a voltage source or a charge geometry. We take some of that energy, we distribute it obviously through the conductor, and this then inductively couples with any charged particle, exerting a force on it, and creates a proportional number of energy momenta within the chem field, in turn creating kinetic energies and magnetic moments. The energy itself is always in the form of charged quanta, and dependent on the charge of the chem field, they can be divergent or convergent within that field, dependent on the net charge of the mass matter itself. Obviously, where these fields come together and equalize, similar numbers of positive and negative charge fields, they form electrostatic fields, or in this case, a magnetostatic field, a bar magnet. The only difference between the electro and the magnetostatic fields is the charge of the chem fields themselves, where they come together or inductively couple. And again, the charge is determined by the equilateral geometry of the field or its quantized angular momentum. All changes of velocity or accelerations under Newton's second law are carried out by changes to the energy momenta within the chem field. These odd-numbered quanta are released to create transitions between square number quanta within each field, or quantum jumps, and upon release they can interact via the weak force to form photons of light, or spectral color lines. Again, as the photons are released, obviously it facilitates a change in the energy momenta of the chem field, which of course relates to a change of force or velocity, or change of momentum, linear momentum in the system, or in case it'll be a change of the total energy momenta of the system in all its forms. We can use the energy momenta of chem fields and electrostatic fields to show us what the forces are between different charged inertial mass matter geometries are. We can use these geometries to explain not only the strength of the force, but the vector direction of the force, whether it's attractive or repulsive, and whether it's a Coulombic force of attraction or whether it's a Lorentz force of attraction between magnetic poles. Again, it's the geometry of the energy momenta that gives us both the orientation of the magnetic dipole as well as the linear forces or the vector velocities that can be created by the specific number of energy momenta within the field. Again, noting that in Tetryonics, where we say energy momenta, we're describing both not only the scalar energy field, but we're also describing the mass property of that energy per second, as well as its angular and linear properties, its equilateral geometry and the square roots. So energy momenta is a broad term for all the forces, scalar and linear, of any energy geometry. We can also show where the fields are superpositioned, the energy momenta within the field, within each field, will create an interactive force where the fields overlap. And this is described as the energy momenta constant squared, and it's a inverse squared law in the cases of electric and magnetic fields. Inverse cubed if you're talking about a dipole interaction. Of course, we can apply these geometries again for the energy momenta to describe all the forces, and in this case we're describing Ampere's law, and we're showing the Lorentz force between charged particles moving in a conductor, and showing the change of either repulsive or attractive forces resulting from their direction of motion. Again, in all the cases, the inertial mass energies of the matter geometries is invariant to the motion. All the energy of motion is stored in the chem field as energy momenta. And we can model this energy momenta as a vector rotation about a point in electrical terms. But in fact it's a direct result of the equilateral geometry of chem fields themselves, or of the quantized angular momentum per unit of time, the charge. As we accelerate particles or change their vector velocities per unit of time, or their momentum in relation to their inertial mass of their matter geometries, we do so by releasing or adding bosons of energy. Again, as all odd numbers, sequential odd numbers, add up to square numbers, so changes between any square quantum level is facilitated by releasing a specific number or a specific boson of odd number energy momenta quanta. As we release these odd numbers, we obviously change the net scalar force of the field, because we're changing the available number of energy momenta in that field to exert a force. But in all cases, any changes of a scalar quantum field require the addition or release of bosons, odd numbered geometries. Of course, if we measure these fields in a longitudinal sense, for their force, their vector forces, we're measuring photons, or triangular geometries, diamond geometry, sorry. Again, in the most basic sense of a quantum, the charged geometry is an equilateral triangle. The linear photons are diamond geometries. You can't relate Planck nu for bosons to Planck frequencies for photons unless you have two bosons to give you a photon. 2-to-1 relationship between bosons and photons. The energy momenta within the photon fields, the longitudinal measurements, is comprised of the equilateral geometries, in this case two masses, because there's two charges to make a photon, positive and a negative. And these positive and negative fields together will create an electrostatic or a magnetostatic field, where the magnetic dipole is enhanced because of the charges, the charge arrangements of energy momenta. But in the case of a photon, there is no particle to fix it at a point and to keep adding energy to the field. So what happens is the photon of energy will radiate outwards at the speed of energy, which is the velocity created by the frequency wavelength relationships of energy momenta within the fields. So we can show that in the case of force, or changes in momentum, or energy momentum within a system, we can express all these things in terms of the quanta within the electromagnetic field by using Planck's constant, We simply divide the scalar field by Planck's constant to give us h nu squared. If we want the square root of that, obviously hf, we can calculate for the linear momentum or the transverse mass energies. We can show that the square of the linear momentum is the scalar energies, and that's a direct result of the number of quanta within the field. Again, the number of quanta, or the Compton frequency, affects the de Broglie wavelength of each Planck quanta, because it's affecting the linear momentum. As we increase the number of quanta, we increase the force available to create a change in velocity. And we can relate the velocity again back to the scalar mass or the inertial mass of any particle using F equals ma, or we can express it as a change in momentum instead of acceleration as just mv. So we can show all the properties of inertial mass, frequency, wavelength, permittivity, permeability, acceleration, velocity, momentum, scalar energies, energy momentum, both as quantized angular momentum as well as linear momentum. All these properties can be shown using equilateral geometries in Tetryonics. The formulations still match, they don't change for the mathematics. What changes is our understanding of the geometry that gives us this math. And in turn, this geometry sets the boundaries for what operations can be performed validly on each mathematical equation. You cannot, for example, say h nu equals E equals hf. You can, of course, specifically say 2 h nu equals E equals hf. Or if you wish to say h nu, you have to specify that it's a generic meaning of number or quanta, and it's referring to the scalar field. Tetryonics, of course, changes this to h nu squared. So we specifically say h nu is a boson measurement, odd numbers, hf is a even number of photon energy, and h nu squared refers to the scalar quantization of energy or energy momenta in the field. Again, the frequency, the Compton frequency, de Broglie wavelength relationships give us the forces or the changes of velocity that each field can create due to its energy momenta. And we can show that frequency and wavelength relationships are again different aspects of scalar or linear measurements of the equilateral geometry, or the alpha of Planck's constant, which is mass alpha. As I said, the changes, odd number bosons added or taken from a field, a scalar square energy field, changes its energy momenta and brings about a change in velocity. And this is the basis for the production of spectral lines within atoms. There's a whole lecture available on YouTube that covers this in a lot more detail. But again, we show the mass, or the mass matter velocity squared relationship for chem fields to the quantized energy in the Rydberg's formula, or constant in this case, for these different spectral lines. Again, the changes in energy and momenta by releasing or adding bosons brings about changes in velocity due to the changing number of available energy momenta within the field. Now that we've defined bosons from photons and their geometries, and chem fields from electrostatic fields, and mass from matter, we can apply this to explain all the properties of wave functions within QED and quantum mechanics. We show all these relationships obviously geometrically within Tetryonics, but in addition to all the previous properties we've described so far as energy momenta force relationships and velocity, we can also show the probability functions of chem fields and EM waves as well. In fact, we can show the probability distributions of inertial mass energy within matter geometries as well, as indicated in this picture, and we can do so geometrically as opposed to strictly mathematical descriptions. Whether it's an EM wave or an energy momenta within an EM wave, or the energy momenta within a chem field, all that changes is the geometry of the net fields. In the case of a chem field, the square root produces a linear force, or a velocity, that's proportional to the number of energy quanta, or the square number of the equilateral field. In the case of photons or EM waves, the velocity is proportional to the frequency wavelength of the energy momenta within the field, and it radiates bilaterally from its source point. If we were to put the energy momenta of this EM wave and apply it to a charged particle, an electrostatic one, we would create an electrostatic field. The particle would remain stationary because the energy momenta would oppose and cancel, creating zero motion or zero momentum. But the particle would still, or the system being studied, would in fact still have energy momenta within its electrostatic field, as well as mass energy or inertial mass energies within its standing wave matter geometry. And again, we can draw all of this in terms of equilateral geometries and measure them either as transverse boson measurements, quantum levels, or as longitudinal photon measurements. Again, in all cases, whether it's a chem field or an electromagnetic wave or an electrostatic field or black body radiation, the energy momenta and the probabilities within those fields are always renormalizable. They always come back to 1 so far as the sum of the probabilities, and the probabilities again is determined by the amplitude of the wave or its square root linear momentum that it can create due to the scalar EM momenta. We can show that whether you take boson quantum level measurements or photon probability measurements of wave functions, any change again is brought about by the release or addition of bosons within the field, and these bosons, because of their odd numbers, always have a single charge of plus or minus 1. Where they combine into square number fields, they have a single equilateral geometry, which again of course is a charged geometry, and this geometry applies throughout Tetryonics, whether it's a chem field, the fascia geometry of mass matter, or in fact the dual boson geometries of photons and kinetic energies. But in all cases where we're referring with wave particle or wave functions, the term particle refers to the standing wave mass energy matter geometries. The wave component of the wave function refers to the mass energies of the chem or electrostatic fields or black body radiation. And again, these distinctions are important when looking for explanations of quantum gravitation and energies within isotopes, etc. Shown here is again the wave function. Whether we measure it in terms of bosons or photons is irrelevant. The energy is the same in both cases. What is changing is the direction of measurement of the energy in the field and its energy momenta. If we apply it to a static particle, it remains a static particle because the energy momenta cancels out. But if we apply all the energy momenta to a charged particle in a single charge geometry or a charged geometry as opposed to a photon geometry, we create motion or a unilateral force resulting in a specific velocity that's proportional to the square root of the number of quanta within the field. This applies to all matter, and the basic equations of E equals mv squared applies to both kinetic and electrostatic and black body radiation fields, and E equals mv squared in the case where m is mass matter geometries applies to chem fields or fields of particles in motion, etc. The distinction obviously being the term of mass for fields versus mass matter for particles, and the distinction is purely a description of the inertial forces between two-dimensional energy and three-dimensional matter, or it's a measure of the inertial mass of particles. Of course, E equals mc squared still applies in the cases where the velocity is the natural velocity of energy, or it's a field, for example, or it's reflective of the standing wave geometry, where the mass energy propagates at the speed of light, or the natural speed of energy within the standing wave. But it is more appropriate to use mv squared in all cases, because the velocity may change. C, of course, only refers to the velocity of the natural velocity of energy in a vacuum. Moving through a different medium will result in a different velocity. Obviously, the extrapolation we can make here that can't be made with the mathematics is that the velocity energy momenta velocity relationship is a geometric relationship. As we increase the frequency of quanta, we increase the velocity or the acceleration of the particle, and this relationship, being geometric, has no limit. We can, in fact, this is one of the rare cases where we can use the term infinity as an expression that we can use any velocity we so choose. We can reach any speed we so choose, providing we have sufficient energy momenta quantum or quanta within that field. Once we have a square number, any square number of energy momenta will produce a linear momentum that is the square root of that Compton frequency. Again, in deference to Einstein's special relativity, it's the energy momenta of the chem fields that creates both the forces of motion as well as the magnetic moment orientation for charged matter in motion. And it's the energy momenta within the chem field that's subject to Lorentz corrections for the mass energies. The matter itself remains velocity invariant. But again, we show the geometry on this page of the chem fields. E equals mv squared. In the case of a complete system, as opposed to the chem field which is described here, if we wish to determine the energy momenta required to propagate or to move a inertial mass of matter forward, we simply say that the kinetic energy is, in this case it would be mv squared, because we have to account for the magnetic moment as well as the kinetic field. This formula is relating to the Ke field only, but the total energy required is the square of the velocity that's required for any given inertial mass. Again, this relates kinetic energies back to F equals ma, and it shows us the Tetronic geometries that create all of these forces and these fields. As I mentioned, the energy momenta of the field, of any scalar field that's required to create a velocity or results from a specific force on a charged matter geometry, is subject to Lorentz corrections, because obviously the mass energy of the field is the result of the energy momenta per unit of time. So as we change the energy quanta for any force that's applied, we of course change the resultant velocity in relation to its inertial mass of the matter that's being pushed. Again, the formulations for Lorentz are correct for two-dimensional EM fields, but they do not apply to standing wave matter. And length contractions should be retermed wavelength contractions, and time dilation should be retermed into charge contractions, or changes of charge, or changes in quantized angular momentum or geometry. Again, showing us that as we add more quanta, we change the de Broglie wavelength of the linear momenta of the systems, so therefore we have to change the physical geometries, and this of course changes the quantized angular momentum, or the mass time, or the time measurements of the system per c squared. or per unit of time. Time itself is charge, or time itself is quantized angular momentum. Charge is mass angular momentum, or Planck's constant. Length, again, is wavelength, not material length of matter. As I mentioned, it's the geometry tells us that there is no limit to the velocities that can be produced, providing we have sufficient energy momenta. And again, it's the square of the energy momenta, or the square root of the energy momenta gives us any specific velocity we're seeking. But we have to relate that to the force applied, well, we'll relate it to the force applied to create the energy momenta through the inertial mass, or Newton's second law. So in the case of a bar magnet, which is historically viewed as being a magnetic field, it is now shown to be an electromagnetic field, with the electric fields and their energy momenta being neutralized. Their photon measurements, they're a longitudinal measurement as opposed to the transverse measurement of the magnetic field. And it's this geometry of the fields and their energy momenta within them that produces the forces on an electron in a conductive loop as it moves about the magnet. If you can visualize the conductive loop as it moves up and down the electromagnetic field of the bar magnet, the geometry and the strengths of the energy momenta within the electric and magnetic fields is constantly changing. Should you stop the motion of the conductor or the conductive loop, the geometry is static, so the force stops. But when motion resumes again, there will be a change in geometry per linear direction, and this change in geometry changes the electric and the magnetic fields in relation to the geometry of the scalar energy momenta within those fields. So what's described in special relativity, or attempted to be described in special relativity, as a change in the inertial frames of electric fields with respect to magnetic fields, and stationary particles with respect to particles in motion or fields in motion, is now explained on a purely geometric basis. And this geometry applies throughout all of physics, as shown in the 5 books of Tetryonics, thoroughly establishing it as the foundation for any mathematical description of these forces. Of course, as noted in the previous 3 lectures, what we've now done geometrically is rebut and disprove relativity theory and the mathematics of it by explaining all these forces and all these motions and fields and quantized energy in terms of equilateral geometries. Of course, you can measure the electromagnetic field of bar magnets, or EM fields, in either a transverse or a longitudinal direction, and in fact they were described for a long time in physics as transverse masses versus longitudinal masses. And again, it's the geometry that gives us the changing magnetic and changing electric fields, and they change in direct proportion to one another as a measure of, and again as a measure of the velocity. The faster you move through this geometry of a EM field or a magnetostatic field, the quicker the change of the electric and magnetic field geometries with respect to each other, and the change of energy momenta within those fields. This gives us our familiar Lorentz force and completely disproves relativity as an explanation for the moving magnet conductor problem. And this is in fact what is happening. The E fields of the magnetostatic field produce, or the energy momenta within the E fields produce, the forces on the charged particles in the conductor that moves about the magnet. Of course, it's not strictly as we see here in the E and M fields. Each quanta has discrete EM geometries, and in fact, as we've shown here, where there are only one quanta as you enter the field, again of discrete E and M field geometries, and then we move to 2 quanta, or 2 photons, so on, increasing up to the maximum amplitude of the field. There's not a scalar, there's a distinct north and south magnetic pole, but within each field there are discrete electric and magnetic poles or fields, energy momenta, and this is borne out when you cut a magnet in half. You don't get a north or a south pole, as you see here in the scalar fields. You get a south, and as you see here, a north pole. The moment you cut the field in half, or the bar magnet in half, you just create a smaller version of the original scalar electrostatic field. It just so happens you can also view in these terms a bar magnet as being a battery that stores the energy of the energy momenta of force within the neutralized EM fields of the bar magnet. So you can view it as a battery. Again, all the mathematical formulations still apply, but what changes is the geometry. The math was correct so far as the geometry it was describing, but it was misinterpreted as a spherical integration of energy, etc., when in fact it's equilateral. Again, just to note the point that Tetryonics is wrong. It's not the spherical distortion of charges due to their velocity that creates that changes the electrostatic field to a magnetic moment. It is in fact the geometry of the EM fields, whether it's an electrostatic, a magnetostatic field, or a chem field. There is no difference. It is the geometry that dictates all the forces and all the interactions, along with the geometry of mass matter itself. And that was Einstein's error. It was an error of perception. He, of course, thought that pi related to spherical geometries, and he knew of Lorentz's formulation for velocity corrections, producing the right amounts, particularly in relation to two-dimensional fields or measurements of light in the Michelson-Morley experiment, etc. And he applied it to mass, energy, matter as a whole within his stress energy tensor. Tetryonics now pulls apart mass, energy and matter into its discrete geometries, explains them from the quantum level upwards, and completely re-explains the creation of magnetic moments for charged particles in motion versus the purely electrostatic fields of charged particles with no motion. So in the case of charged matter geometries, the matter itself is neutral in its stationary form with no field. In the case where it has blackbody radiation or an electrostatic field, it still remains neutralized, but contains a specific geometry of energy momenta within the fields that contain convergent and divergent directions of action for the Planck quanta themselves. This creates our law of interaction for electrostatic fields and for charged particles in motion with respect to each other. And of course, it shows that electrostatic fields have no magnetic moment, just an E field, but when in motion they possess a magnetic field or magnetic moment, which of course is the result of the energy momenta of motion stored within their chem fields. Again, all these fields, irrespective of whether they're electrostatics or chem fields or blackbody radiation, follow E equals mv squared, or we can quantize that scalar field, classically described as E equals mv squared, using Planck's constant to give us h nu squared for the equilateral geometries of the energy quanta, again with Planck's constant h also being shown in Tetryonics to be mass alpha. The fields themselves, the energy momenta within the fields, as we described in the previous lectures, can be reinterpreted in terms of the vector rotation of electric fluxes in zero-point fields that make up the energy momenta in the chem fields or in the electrostatic fields or blackbody radiation. And in doing so, we can show physically, or in a physical model, how the fields of force transfer energy momenta, both in an electrical sense, as described on this illustration, but if you were also to draw them as just the equilateral geometries, you can see that the equilateral geometries are just quantized versions of the scalar field, and it's the geometry that gives us our changing electric and magnetic fields, and it's the square root of these fields that gives us the linear momentum or the force vector. We of course show that in the case of force there are no virtual particles within Tetryonics or within physics, full stop. All the actions of force and interaction of force fields is completely done through the superposition of the energy momenta in discrete chem fields or electrostatic fields, where the fields superposition in the longitudinal direction, but over their E fields they create a squared E field or a coulombic force between charges. Where they interact laterally or in a longitudinal, a transverse sense with the magnetic fields superpositioning, they create a Lorentz force between either static particles again or particles in motion within in conductors, etc., or in accelerators. All of these energies, superpositioned energies, are just the square of the energy of one kinetic energy or the other within the chem field, either electrical, magnetic, and they can be described in terms of their mass velocities or their momenta velocities, their mass velocities. Again, two different formulations for the same thing. One's looking at the linear properties, the momenta velocity, momentum with the velocity it can create, versus the mass or the energy per unit of time that creates a specific velocity. This can be rationalized as either E squared equals m squared v to the fourth or p to the fourth, or we can redraw them using equilateral geometries of Tetryonics as shown here, in which case the kinetic energy becomes kinetic, either form of kinetic energy becomes kinetic energy squared, and it's the alpha of the Planck quanta, the mass alpha, that gives us the strength of force. As we increase the number of equilateral mass energy geometries by the Compton frequency, we increase the alpha of the fields interacting, and again the alpha is the equilateral geometry or the fine structure coupling constant, familiar to all in quantum electrodynamics, and it's the interaction of the geometries, either convergent or divergent, that gives us our laws of force and the directions of force in physics. This field's traditionally been calculated from a mathematical perspective, and it's given an incorrect number of the inverse of 137. In fact, the number is the inverse of 132, and this is derived from the theoretical basis of equilateral geometries in Tetryonics, and in fact alpha per c squared gives us quantized charge, or 1.335 by 10 to the minus 20 coulombs. Of course, 12 charges interacting, or 12 Planck alpha, will give us a charge geometry of an electron, and this will give us a elementary charge of -1. So Tetryonics shows that the alpha constant that's been sought for, the coupling constant, hidden within Planck's constant, mass alpha, or h, in fact has a theoretical value of exactly of the inverse of 132.6291192. The reason for the discrepancy, of course, is the fact that in attempting to calculate it mathematically, we're calculating from observed particles, and then we're using ever increasingly more elaborate experiments to refine these measurements. Unfortunately, in the case of physical experiments, you can't completely exclude external EM fields and their energy momenta, such as electrostatic fields or blackbody radiation, or the energy of motion. These all affect the measured forces and the measured constant. The secondary problem that presents itself by using the mathematics is that, of course, in the case of taking physical measurements to determine how accurate the number is, we're working towards a known answer. And in fact, what's happening is that with QED, it's becoming increasingly called the most accurate description of quantum mechanics available to humanity, because it's accurate to 12 decimal places. Tetryonics shows that in this case it's accurate to 12 decimal places for the wrong number. Again, it should be 132, not 137. And that's borne out by charge and the strength of the coupling constants for coulombs and Lorentz forces, etc., and gravitation itself, as will be discussed in future lectures. But Tetryonics completely rewrites QED and its accuracy from a mathematical perspective, and shows it from a geometric perspective, where the alpha of Planck's constant, mass alpha, is what gives us our coupling constant for various force constants. We can apply this, as I've just said, to Coulomb's constant or to Newton's gravitational constant for force. In either case, we're measuring force, and the force is determined by the number of energy quanta per field of each charged particle. In the case of Newton's force, it's a neutral particle, mass matter. Again, even neutral particles of mass matter or inertial mass matter are made up of charged geometries or charged quanta. So we can use equilateral chem fields to model the energy momenta and the forces between large scale matter, but we don't have a interactive field. We have a convergent or an attractive field, strictly convergent. Whereas in the case of Coulomb's force, we have a interactive field due to the divergent and convergent energy momenta within the field. Newton's formulation and Newton's constant can be modelled using equilateral geometry. However, this is not physically what's happening at the quantum level, and again, this is discussed in detail in another lecture. But it does give us the right results, because mathematically the geometry can represent the mathematics and show what is going on. Of course, we can use equilateral geometries to give us things like electric permittivity, magnetic permeability, the inverse squared law, convergent acceleration due to gravity, the scalar fields, the force that these scalar fields can create, or the specific velocities. And we can apply this to matter or force laws in all cases, whether it's charge or gravity or Lorentz forces. They can all be described using the equilateral or pi radian geometry of Tetryonics, and particularly the forces described where we have superpositioned fields. It's the superpositioning that gives us our field of interaction. And again, alpha itself, or the alpha fine coupling constant, is in fact alpha of, or the equilateral geometry of Planck's constant, which of course is mass alpha, kilograms square meters per second. Stripping or ignoring the energy component and the mass component, looking at just the alpha per second, or unit of time, is the same as alpha per c squared, and this gives us our quantized charge values, positive or negative, which make up all mass energy matter within our universe. Again, showing that it's the equilateral geometry that's the key to understanding the force created by increasing or decreasing energy momenta within any charged equilateral field. Newton, of course, described all the changes of acceleration as changes of linear momenta per unit of time, or mass velocity per time. Leibniz, on the other hand, described it in terms of the scalar energy momenta. Newton, P equals mv. Leibniz was E equals mv squared. 1 is the square root of the scalar, or the scalar is the square of the momentum. Again, all geometric relationships, and as is the case in most fields of physics where there's disagreement or different results or different forces being created or measured, it is simply a different measurement of the same geometry. Newton was measuring the square root and changes in the linear momentum. Leibniz was measuring the total energy momenta within the field and how it changed with relation to the velocity. Brought about a lot of heated discussions between the two, and the discussions remain to this day as to which is appropriate. Again, in Tetryonics we can choose either form, and we can choose how to measure things or how to describe them geometrically to create the mathematics that we use. But at all times we have to be careful not to use classical interpretations of the math or graphing as shown here. In this case, the square root function is shown as a curving line, whereas in Tetryonics it's shown as simply the amplitude or the height of any of the scalar EM energy momenta. Again, highlighting different formulations for energy, measuring different geometric properties of the same field. And in fact, where it comes to QED, we look at the quantized energy in the same field, and we assign probabilities depending on their whether it's a transverse or a longitudinal measurement. So Tetryonics can bring all of classical physics, quantum electrodynamics, quantum mechanics, chemistry even, as well as general relativity and the statistical probability of QED and QM back to a simple equilateral geometry. All these features, all these formulas, all the math in fact, where it's correct for physics, can be shown in the equilateral geometry of energy momenta within fields, whether it's a force or whether it's a scalar property of the field. It all relates back to the energy momenta measurements of Planck's constant, or particularly relates back to alpha, the equilateral geometry. In this case here, we've shown how Euler's formula, long considered to be a transcendental formulation of irrational numbers, exponents, trigonomic functions, is in fact no more than a description of charged energy momenta in either charged fields or within EM waves. Applying it, we can see the sine-cosine relationship to the energy, which is exponential, again following V squared. The electric to the magnetic of the fields is a sine-cosine relationship, and as we move laterally from the amplitude of the wave, measuring the photons, we have a sine-cosine relationship between the photons themselves. That's described here. Again, breaking it down, we can see that e to the I pi equals -1. That's no different than saying the exponential energy in the negative charge geometry gives us -1, or can be described as -1. Again, where we describe it as the square root of -1, which was never taken to be a serious number, because you can't, even though you can mathematically state the square root of -1, you can't give a physical answer to it, because any number, positive or negative squared, will always yield a positive number. In Tetryonics, however, we can say the negative charge field has a discrete square root, which is the linear momentum of the field, and it is most certainly physically different and completely opposite to the square root of the positive charge field. squaring the linear momenta of the negative charge field, or the squaring the square root of the -1, will still give you -1 in the case of physical geometries, where it won't in the mathematics. Again, just another example where the mathematics models it correctly, but breaks down in its grammar where it does not have the correct geometry for that mathematical formulation. Tetryonics now shows how Euler's formula in fact describes the charge geometries of EM waves and photons. The same equilateral geometry as we've discussed can be applied to give us calculus. Again, as Leibniz and Newton both developed independently and argued over for many, many years. One is a scalar measurement of the energy momenta in the field, described as differential calculus, whereas Newton measured force as a change or an acceleration, change in linear momentum of the system. One's the square root versus the scalar, and developed a similar math to describe the forces. Of course, both their formulations weren't in terms of equilateral geometries. They were just rectangular sections of area, or integrations of area underneath the curves produced by the force, as measured in terms of momentum or energy. Tetryonics takes a completely different view of the mathematics and the geometry that underlies the mathematics, re-expresses calculus in terms of equilateral energy geometries, and explains force in terms of the scalar energies as well as the square root linear momentum of those energies. And as you can see here, and of course it yields not only F equals ma and E equals mv squared, but we can quantize that using Planck's constant to give us nu, or mass alpha nu squared, or mass alpha or mass velocity squared as a relationship, thus uniting classical and quantum mechanics yet again through equilateral geometries, and allowing us to calculate for inertial mass using the electrical flux properties of quantum inductive loops. In the case of differentiation, obviously we're just measuring changes of one physical parameter against the other per unit of time, or changes in time. In the case of Newton's F equals ma, we're measuring the changes in linear momentum, mass velocity, per unit of time. Velocity obviously a change in distance per unit of time, or per change of time. And the acceleration just being the change of distance, or change in velocity, per unit of time. So we have meters per second for distance per unit of time for velocity, and for acceleration we have meters per second squared for acceleration. Classically stated, not always intuitive as to what they mean, particularly where it comes to seconds squared. In Tetryonics we now show second squares to be a volumetric measurement of time, or c to the fourth, versus per second, which is c squared. One is mass, the other one is inertial mass of matter, or a measurement of inertial mass of a system. Obviously F equals ma gives us the inertial mass of any system. Fails to distinguish between mass and matter. Tetryonics clearly distinguishes between mass and matter, and the inertial masses of both through the geometries. And of course we can see here in the case of F equals ma, to change the velocity of a system we have to change the number of energy momenta, quanta, within that field, and it's the net energy momenta, or the square root of the squared number of quanta, that gives us the force. So changes in velocity or acceleration require the release or addition of bosons, which of course brings us not only from classical into quantum, but leads us to the photoelectric effect and chemistry, all within the same simple geometry explaining the forces created by the energy momenta within any charged geometry. And again, as Newton said, if we don't change the energy momenta within the field, or no force is added, a body in uniform motion will remain in uniform motion until an external force acts upon it to add or release bosons, of course. And that follows the exact same formulation of electrical energy in an inductive loop, coincidentally. Again, backing up alpha as being part of Planck's constant, mass alpha. In the case of integration, as I said, normally the area under the curve is used to calculate or integrate for the forces and solve for them. In Tetryonics, what we're actually doing is integrating the Planck quanta within the field. We can see not only the number of quanta that's required to create a specific velocity or an acceleration by changing the number of quanta, but we can add those quanta together to give us a scalar field of energy for any change in, or any force that needs to be exerted to achieve these changes. Additionally, we can also show via the quantization of these scalar fields and forces the statistical probability and energy distributions for transverse and longitudinal masses within these force fields or fields of energy momenta. And again, the integration is simply summing the finite number of quanta, not the infinite as shown in classical formulation of integration. We have a finite number, Compton's frequency or nu squared, velocity squared in the case of classical measurements of force mass. But in either case there is a finite number. It is never infinity. And this is particularly important when you're looking at spectral line series, for example, where we can specify using tetronic geometries the physical energy levels to any force or any ejected electron within the atomic nucleus. We can obviously use tetronics to give us fractional numbers as expressed in these spectral lines, a quarter or any fraction of a square number as expressed in Rydberg's formulation of 1 over n squared minus 1 over n squared for the initial and final energy level transitions. These transitions or jumps between energy levels, square number energy levels, are done by releasing bosons that create photons of spectral lines. And of course, by releasing the bosons, we are changing the net energy momenta of the field, and of course the force that the field can create, and its velocity or acceleration changes. We can draw all these fractional changes using equilateral geometries, and in this case you can see that ignoring the numbers at the top of the triangle, the bottom 3 triangles are 3/4, all 1/4 of the total triangle. The top triangle, the top quarter, of course can be divided again in half, or in quarters, and that, of course, the top 16th of that triangle then, or the top quarter of that second triangle, can be divided again and again, and we can repeat this process onwards and onwards. Of course, we never reach infinity, as is classically formulated in the mathematics. We reach a finite solution. Again, no infinities in Tetryonics. But in doing this, we just geometrically show what a infinite sum series would look like. We can show, of course, that 1/3, which is what we discussed, can be the addition of a quarter plus a 16th and a 64th and 256th and so on. It can be approximated using this formulation. And again, we can do the same thing because they're all expressions of square number changes or quantum level changes, and we can apply this formulation to spectral line series. As we mentioned, all of the force laws we've now just covered are equilateral geometries. They are not right angle triangles as classically drawn in relativistic explanations of the total energy momenta in any field, where in this case we see the right angle triangle showing us the relativistic energies expressed as matter plus kinetic energies, and we see a sloping curve for the momenta relationship of the total scalar energy momenta versus the matter content or the standing wave mass energies. Tetryonics not only separates these terms out, it gives them distinct equilateral energy momenta geometries. And again, it redefines them in terms specifically of the energy terms, redefines them in terms of Planck's constant or mass alpha, the equilateral energy geometries. Again, mass being energy per second, alpha being the geometry or the charge, and nu squared is the number of quanta, so the number of equilateral mass energy geometries gives us the energy, and that's obviously equivalent to mass velocity on a one-to-one basis geometrically. All of these relate back to force. So for any force that's applied, a change in momentum or a change in velocity must occur, F equals ma, and accordingly E equals mv squared. So in order to effect this force and create these changes in momentum velocity, we must add specific square number of energy momentum quanta, or equilateral mass energies, to the scalar field to effect this, or to bring about this change. It's these changes of mass energy quanta within the scalar field that we can model as a flux of electrical energy in a ideal quantum inductor or a 0 point field, Planck's constant, again where the flux is simply representing the equilateral geometry. It's another form of angular momentum, quantized angular momentum specifically. But either way it's drawn, it shows us quite clearly an analogy between the energy stored within inductive loops and inertial matter, inertial mass within mass energies and within matter itself. So as each Planck quanta, which is just mass, quantized angular momentum, which is the equilateral geometry, so as each quanta is added in specific geometries to create our square number geometries, it resists this change, because once the circuit is established, just like the normal macroscale inductive loop, it resists addition of energy to the circuit, and it does not like having energy taken away. This is what we describe as inertial mass, or in the case of electric inductive loops, we often describe inductors as the mass equivalents. So we can describe inductors as mass because they do resist change to the energy in their circuit. Of course, this loop does not exist. It's equilateral geometries again for Planck's constant. And what is happening is that the square energy levels of the equilateral geometry obviously require energy to be inputted. You have to use a force or do work to add energy. And these energies can only be added in odd-numbered bosons. You can't add a square number, you can't add an even number. It has to be a odd number transverse boson that is added. And it has to follow the sequence of odd numbers. You can't get to 11 and then add 15, nor could you add 9. What must be added is 13, and only 13. This forms, of course, the basis of inertial mass and resistance to changes in velocity in Newton's formulation. It also is the basis for the photoelectric effect, where only specific wavelengths of light, according to the boson frequencies, will allow transitions between quantum levels. The wrong color or wrong frequency of light will not facilitate a change, no matter how intense that light is. If it's not a 13 quanta boson and you're pumping in 11s or 15s, no matter how many you pump in, there will be no transition. The transition will only occur when you have the right specific frequency of light or bosons being inserted into the energy. At that point it will change, but again, it's not a simple change. In order to add that energy to the geometry, you have to change the frequency, obviously, of the field by adding the energies, and obviously you also have to reduce the wavelength of all the quanta within that field. So again, it will require work to compress the wavelengths of the Planck quanta within the field. So there's a resistance This is what we call inertial resistance to force. And again, it's described through equilateral geometries of bosons, photons, and scalar energy fields in relation to force, mass, and the acceleration that's created. So we can in fact now show that the equilateral energy geometry or mass energy geometry of Planck's constant is the basis for inertial mass within all of physics. I often find it handy to view it as this inductive loop of energy, inductive flux, because my background is electrical engineering. So it's very easy for me to see the inductive loop and immediately relate all the electrical properties of inductors and short-circuited inductive loops to the equilateral geometry. And in fact, that's how I first saw it before I finally, even in my own mind, fully accepted the equilateral geometry being angular momentum. But you can drop that out. But it is a very handy learning tool, particularly for those that are familiar with electrical engineering terms and formula, etc., in order to build practical models and understand the physical properties of Planck's constant and quanta in general. Obviously, it doesn't matter how many quanta you add to a scalar field, as we've discussed before. All that changes is the wavelength of the quanta themselves, the energy content of the field, and the energy momenta within that field. And that, of course, has a bearing on the acceleration that can be produced for any particular inertial mass. So not only is there inertial mass within the fields themselves, whether they're two-dimensional or three-dimensional standing waves, there is also the fields themselves also contribute, in the case of the charged geometries of matter, as inertial mass energies within matter itself, hence the term mass energy matter. But in all cases, it's Planck's constant that's defining the inertial mass at the quantum level. Of course, whether we take transverse or longitudinal measurements of the energy momenta within the field, they always add up to the same scalar field of energy or mass equivalent. But what changes obviously is the number of quanta. In the case of bosons or Planck quanta, we have individual quanta, whereas in the case of photons we have dual boson quantums. Again, h nu versus hf. Again, distinguishing between heat laws and photoelectric effect. Of course, no matter how we measure it, whether it's transverse or longitudinal, or whether it's individual quanta or photon quantums, either way, whenever we calculate the quantum for any particular amplitude of wave, we know that the energy momenta quantum within that wave will be the square of the amplitude, or the square of the linear momentum of the wave. And we also know that we can work out the normal distribution or the bell curve of these distributions, irrespective of whether we're taking single or dual quanta measurements. And we can renormalize these probabilities that are generated back to 1, as in a single unified scalar field of energy. Again, showing that it's the equilateral geometry in this case, or the Planck's constant, that gives us the number of quanta and gives us the distribution of energy within the field dependent on our direction of measurement. In describing things as a bell curve, obviously the equilateral geometry is angular, it's equilateral, whereas the bell curve is a smooth curve. This is simply the result of averaging out macro scale measurements of equilateral quantum energies. It's a reflection of our level of accuracy, if you like. This of course applies irrespective of whether you're talking about Planck quanta, charged geometries, or electromagnetic fields, or blackbody radiation fields, or chem fields, or even gravitational fields. All the mass, energy, matter in our universe, everything within empty space, is created by Planck quanta, equilateral mass, energy, momenta. Again, we can measure the momenta in terms of linear momentum or angular momentum. We can measure the EM fields and its properties in terms of its transverse or quantum levels, its bosons, or its longitudinal amplitude, probability, linear momentum. In all cases, the geometry tells us what we're measuring and gives us the mathematical formulation, not the other way around. And this is where mathematics, although it's rigid in its approach and its use as a language, is lacking a formal grammar to show how this mathematics should be applied and where it is in fact incorrect. Tetryonics rectifies this, obviously. It also shows us, in this case, in the case of all EM waveforms with energy momenta, longitudinal measurements or photonic measurements of the energy of the field gives us a different wavelength and a different properties, different quanta, to that of boson measurements or transverse measurements of the same energies. The energy momenta, of course, is also focused in the square root of the energy in the direction of propagation, and that's a longitudinal direction. Again, there's also a distinction between the energy momenta within a EM wave and the various types of EM waves, either transverse or longitudinal waves. And the mathematics gives us no clue as to what's going on, hence why we've ignored longitudinal waves for over a century since Tesla discovered them. And the mathematicians, in fact, insist that the claims of Tesla technology is incorrect because the electric and magnetic fields are transverse to each other or orthogonal, and they propagate in a transverse direction to the direction of velocity of propagation. Tetryonics shows you that while this is true and mathematically correct, there also exists another form of transfer of energy momenta, and that is where the linear momentum of the EM wave shown here is in the same direction and not transverse to the direction of propagation, and that is the longitudinal wave, longitudinal EM waves that Tesla was describing in his work. These haven't been described. The mathematics is identical. The only thing that has changed is the direction of linear momenta with respect to the direction of propagation. It's a polarization, if you like, of one waveform to the other, transverse to longitudinal, or vice versa. But in all cases, we can now describe both forms of waves and all their physical properties and the forces that they exert using equilateral Planck quanta. And that's what we do on this page. We show all the functions: velocity, quanta, frequency, voltage, quantum levels, wave amplitudes, probabilities, linear momentum, scalar E fields or scalar M fields, the transverse portion of the M versus the longitudinal of the E. All these things, how changing electric fields produce changing magnetics. All these things are shown using equilateral geometry, and more importantly, the equilateral geometry is very specific about what operations can and cannot be done geometrically, whereas the math is less specific, and that's what leads us to many erroneous assumptions about multiple dimensions or what the wave function is actually telling us about the probability of particles in relation to wave particle duality, etc., and has clouded the physics. While the mathematics is an extremely accurate way of measuring observed results, it offers no understanding of the underlying forces and geometries at work that create these physics. Again, with the normal distributions for energy momenta, we show that mathematically they've been described as bell curves or normal distributions, whereas in fact they are equilateral geometries. And again, we show how all of Gauss's charge formulations and the energy formulations of Leibniz and the momenta formulations of Newton are all described within the equilateral geometries of Planck quanta and scalar EM fields. We of course show how the mathematical equations in cases that have not been explained, i.e. in this case Euler's formula, can in fact be applied directly to the equilateral geometries to give us an explanation for impossible numbers like the square root of -1, and for a basis of where relativity is generated from within physics itself at the quantum level. We can, interestingly enough, rearrange square matrices to be, of course, equilateral geometries. In this case, what I've done is I've taken the typical square matrices of relativity of 1 by 1 through to 8 by 8 quantum levels and rearranged them in terms of their energy momenta or their EM properties. You'll see that the electric and the magnetics are indicated by their blue for the electric and the aqua for their magnetic fields, and of course the square root of these equilateral or square matrices is the linear momentum, so it's highlighted in a fuchsia. By doing this, it's not as easy for people that are accustomed to squares being squares, but what it does do is it reflects the equilateral physical geometries of energy and momenta at the quantum level. So when we develop our square matrices for describing energy fields, for example, scalar energy fields, square scalar energy fields, upon applying the numbers for the various values for the electric and magnetic field, we can immediately not only determine the strength of the field, we can also show the electric and magnetic quantized properties as well as its linear momentum, purely from the arrangement of the numbers. Again, this is in complete difference to physics or mathematics as it's physically described in physics at the moment. It flies in the face of our natural interpretation or understanding of what a square number is. But the benefits that come from that are obviously immense, particularly where you're doing very intense calculations. Of course, all the square matrices drawn here are simply number representations of the field, the quantized angular momentum and the energy, or the Planck's constant, of the scalar field here. So whether it's a positive or negative charge makes no difference. We could in fact encode all that information in there. I'll leave it to the mathematicians to see if this is of any benefit in their learning and it has any application in mathematical fields. So that'll bring us to the end of explaining Planck mass energy quanta and how they bring about fields of force within quantum mechanics and QED particularly. Obviously this applies throughout and there'll be other lectures and discussions on it, but at this stage it's given us a good grounding as to how the equilateral geometries of energy, or the Planck quanta, combine within the charge fields, or the equilateral geometry scalar fields, to give us force and laws such as interactive Coulomb's force, Lorentz forces, and strictly attractive gravitational forces. If you have any questions or you seek any further information, please feel free to drop me a line or an email, and I'll give you some specific examples to answer your queries. Thanks for your time, and I trust